In a binary star system, two stars orbit their common center of mass, and the path is fairly simple. But if a third object joins in, everything changes. Now, each body's motion is pulled by the gravity of the other two. The path is no longer a simple ellipse. It becomes chaotic and hard to predict. This is the famous three-body problem in astronomy. It's been a puzzle for scientists for centuries and is one of the most challenging problems in celestial mechanics. So, why is the three-body problem so hard to solve? We have to start with Isaac Newton. In 1687, Newton published his Mathematical Principles of Natural Philosophy, introducing the law of universal gravitation. This law gave a precise mathematical description of how two bodies move under each other's gravity. For example, Earth's elliptical orbit around the Sun, or the Moon's path around Earth. Both can be calculated accurately using Newton's formulas. A two-body system is like an elegant cosmic waltz. Clear steps, steady rhythm. But when a third body joins this dance, everything gets complicated. Each object feels the pull of the other two, creating a tangled web of gravity. The path stops being a simple ellipse and turns unpredictable. Newton's laws are powerful, but in a three-body system, they can't give an exact solution. The difficulty comes from chaos. In a two-body system, small changes in starting position or speed lead to small, predictable changes in the path. But in a three-body system, even the tiniest difference, like a planet's position being off by just 1/1000th of a millimeter, can lead to a totally different outcome over time. This is like the butterfly effect. A butterfly flapping its wings might trigger a hurricane far away. In a three-body system, a tiny disturbance might throw a planet out of the system, cause collisions, or completely change an orbit. For centuries, mathematicians and physicists have worked to crack this problem. In the 18th century, Euler and Lagrange developed new mathematical tools and discovered patterns in special cases. Lagrange found 5 special balance points, now called Lagrange points. At these spots, a smaller object can stay in a stable position under the combined gravity of 2 larger ones. These points have real uses. For example, the James Webb Space Telescope orbits around the Sun-Earth L2 Lagrange point in a halo orbit that keeps it stable for observations. By the late 19th century, Henri Poincaré's work revealed the chaotic nature of the problem. He proved that the motion of 3 bodies cannot be predicted with one simple formula, laying the foundation for chaos theory. But scientists didn't give up. With the power of modern supercomputers, they've found around 12,000 stable 3-body orbital patterns under special conditions. These are rare exceptions, but they show Newton's laws can still work in specific cases, and they highlight how computational science can tackle complex problems. Still, precise prediction for the general case remains unsolved. In short, the 3-body problem is more than a scientific puzzle. It's a symbol of human curiosity. It reflects our drive to find order in chaos, to search for answers in complexity. It shows the limits of our knowledge, but also how challenges push science forward. And in the real world, the 3-body problem has many uses. In astronomy, it helps scientists understand the dynamics of star systems or planetary systems, especially the stability of exoplanet orbits, where multi-body gravity matters. It has also advanced the study of chaos theory. The 3-body problem is a classic challenge in science history. It reveals the complexity of motion in the universe, and it has driven progress in mathematics, physics, and chaos theory. We still don't have a general, exact solution, but through simulations and studies of special cases, scientists continue to explore its mysteries.